In this last lecture of Chapter 10, we're going to look at partial pressures, mole fractions, and the kinetic molecular theory. So we have another gas law we're going to look at here, which is Dalton's law of partial pressures. And yes, this is the same Dalton that we talked about way back at the beginning of the semester when we talked about atomic theory. Dalton came up with this idea that if we have a mixture of gases, the total pressure of that mixture is going to be equal to the sum of the pressures that each would exert if it were alone. So if we have oxygen, nitrogen, and carbon dioxide in 3 separate containers, and they each have a pressure of 1 atmosphere, if we put those 3 gases together, then we would just add their individual pressures. 1 plus 1 plus 1 would give us a total pressure of 3 atmospheres. So this allows us to determine the pressure of a gas or a mixture of gases when we know the individual pressures, or it allows us to be able to calculate the individual partial pressures of the gases in a mixture if we're given our total pressure and our mole fraction, how much of each gas we have. So that's Dalton's law of partial pressures. So here is an example. A mixture of 6.00 grams of O2 and 9.00 grams of CH4 is placed into a 15.0 liter vessel at 0 degrees Celsius. What is the partial pressure of each gas? What is the total pressure in the vessel? So we've got to figure out our partial pressures and the total pressure. Now, we're given grams. We need moles because we're not given the pressure of these gases. We have to figure out what they are and what the total pressure is in the vessel. But thankfully, they've given us volume and temperature to help us do that. So the first thing we're going to do is convert the mass of each one of these to moles. So I use my molar mass, and with this amount, with this mass of each gas, I have 0.1875 moles of oxygen gas and 0.5607 moles of methane, CH4. I don't have a pressure here, but I have N, my number of moles, I have temperature, and I have volume. So I can calculate pressure. So what I do is calculate the partial pressures of oxygen and CH4. And so you'll kind of see my notation there. I've got a P sub O2. And when we see a P sub O2, that's our pressure of that particular gas. And a lot of times you'll see that when we're doing these partial pressure equations. So I calculate my partial pressure of oxygen by plugging in my number of moles of oxygen times my ideal gas constant times temperature, which I converted from 0 degrees Celsius to 273 Kelvin, divided by the volume, which they told me is 15 liters. So my partial pressure of oxygen is 0.280 atmospheres. Now, it's not shown on here because I ran out of room, but I do the exact same thing for the methane and get the partial pressure of methane of 0.838 atmospheres. They also want to know total pressure. I just add them up. Remember, that's Dalton's law of partial pressures. I have 2 gases in my mixture. I add up the pressure of each of those, and that gives me my total pressure. So when I add those together, my total pressure is 1.12 atmospheres. So again, this is one of those that can make you freak out, but just stop and think about what you know, what equations you know, and how you're going to get to what you have. Okay. So we first had to convert mass to moles, use the ideal gas law to calculate the pressure of each gas, and then add up those partial pressures to get our total pressure. Now remember, at the very beginning of the part 1 lecture, I told you that one of the things that makes gases behave the way they do is because they feel like they're virtually alone, right? So the gases behave independently of one another, even though they're in a mixture. And even though that's a homogeneous mixture, the gases are going to behave independently. So we can relate the amount, meaning the moles, of a given gas in a mixture to its partial pressure. So we've got this derived equation here again. And basically what I've done is just solved for pressure. And I've got P1 over P total, so my pressure of a gas, whatever gas it is, divided by the total pressure of the gas. And you see it's equal to N1 RT over V divided by NT RT over V. Okay, what did I do here? All right, so what I did is I solved for pressure in my ideal gas law. And pressure is equal to nRT divided by V. But I want to compare. I want to compare the partial pressure of one of the gases in my mixture with the pressure of the total mixture. So I set up my equation, so I have P1 equal to N1 times R times T divided by V, divided by, on either side, PT equals NT, which is total number of moles, times R times T divided by V. Well, my RT over V cancels. I didn't show that on here, but that cancels. And when the RT over V cancels, I'm left with P1, so partial pressure of gas 1, divided by the total pressure is equal to the number of moles of gas 1 divided by the total number of moles. And that is read as the mole fraction of gas 1, which we assign a variable of X sub 1. So X sub 1 is equal to moles of compound 1 divided by total moles. Okay, now keep in mind, I know this is a lot to take in. And your book does give a little bit more explanation. But what we're trying to do is relate the number of moles of gas to its pressure. We know that's Avogadro's law. Okay, we already did that. But now we're looking at partial pressures. We're looking at when we have a mixture of gases. So we have to consider the moles of compound 1, meaning the moles of gas 1, divided by the total moles of gas that are present in the mixture. And that is called our mole fraction. Okay, and that's represented by X sub 1 there. Okay, it's going to make sense here in just a second. So when we combine these equations, we get X1, so our mole fraction, times total pressure. So we can use the mole fraction to determine our partial pressure of our gas. Okay, when we solve for P total there. So if we take we solve for P1 there. We can take our mole fraction, multiply it by the total pressure, and that will give us our partial pressure. So let's look at that problem. Again, I think it'll make sense when you look at the problem. All right. A study of the effects of certain gases on plant growth requires a synthetic atmosphere composed of 1.5 mole percent CO2, 18.0 mole percent O2, and 80.5 mole percent argon. Notice it doesn't say mole. It says mole percent. So if you see mole percent, that means mole fraction. Okay, so you're not just going to use the number of moles. We've got to use our mole fraction. So in order to get our mole fraction here, we take our mole percent and divide it by 100. Right? Because anytime, we're trying to make a percent, we multiply by 100. Well, since we're trying to get a fraction and not that percent, I divide by 100. Okay? Because they want me to calculate the partial pressure of oxygen. So that's why I use the 18.0 mole percent. So now I have my equation, my P1. So my partial pressure of gas 1, in this case O2, is my mole fraction of O2 times my total pressure. So I get my mole fraction. 18.0 divided by 100 gives me 0.180. There's no unit on that. Times my pressure I was given, 745 torr. So my partial pressure of oxygen is 135 torr. Okay. Makes sense. It makes sense. Because if I look at the total pressure is 745, and I have roughly 20% oxygen, 20% of 745 is right around 150. So I got 134. So that's spot on. Okay. So I've calculated my partial pressure of oxygen. That's part A. If this atmosphere is held in a 121 liter space at 295 Kelvin, how many moles of O2 are needed? So I got my pressure of O2. Now they want to know moles of O2, and they've given me volume and temperature. So I convert my torr that I calculated there in part A to atmosphere, and that gives me 0.176 atmosphere. I plug all that in, and I solve for N, my number of moles, and I get 0.879 moles of O2. So again, don't let the equation throw you. Okay? Don't be dismayed by the mole percent there. You know, when you see mole percent, don't freak out and think, oh gosh, I don't know what to do with this mole percent. Yes, you do. That's your mole fraction. And you know how to convert that then to a decibel so that you can multiply that by your total pressure to get your partial pressure. Okay? And then use that to solve for your number of moles. So a lot of these problems are going to be two-part problems. So I don't want you to, give up on these. If you ever get confused as you're working on your assessment or anything like that, all you have to do is ask, and I can point you in the right direction. Okay? So don't be alarmed, don't be upset, don't just give up and leave them blank. Try to work them, and if you can't, then just ask me for help. Okay? So that is partial pressure and mole fraction. Now the last thing we're going to look at is the kinetic molecular theory. So the ideal gas equation explains how they behave when we look at the relationships between pressure and volume and temperature and moles, but not why they behave that way. That's where the kinetic molecular theory comes in. It is going to allow us to explain why gases behave the way they do. So the first thing we have to consider is that gas molecules are in constant random motion. Okay? So gas molecules, we know that they have kinetic energy because they're spread far apart, and in order to be spread far apart, they have to have energy to do that. Well, they maintain that energy by being in constant random motion. So gas molecules are never still. They're bouncing off the walls of their container, they're bouncing off the walls, or they're bouncing off one another, they're going all over the place. Okay? And it's random. We can't predict where the gas molecules are going to go. It's completely random motion. So they're going to have collisions all over the place. So that's the first thing, is that they're bouncing around all over the place, and it's a completely random motion. The combined volume of all molecules of the gas is negligible relative to the total volume of the container. This is because they expand. So if we collect all of those molecules of the gas and combine that all up, it's going to be tiny. It's going to be minuscule in comparison to the total volume of the container. So we just say, well, it's negligible. Like, it doesn't even matter. And that's why we can say that the volume of a gas is equal to the volume of the container that it's in. The other thing is that because their volume is negligible, And because they're in constant random motion, attractive and repulsive forces between the molecules are negligible. They're not going to be still long enough. They're not going to be close enough long enough to be attracted to or repulsed by one another. So there's going to, in other words, there's not going to be any intermolecular forces at work. Okay, we're not going to start having bonds that are forming between these gases because they're constantly moving. So they can't be attracted or repulsed. Okay. Now they're going to collide. As they're bouncing around, they collide with each other, they collide with the walls of the container. Energy can be transferred between the molecules during the collisions. But as long as the temperature is constant, the average kinetic energy does not change over time. In other words, we have an isolated system. Okay, we talked about those last week. That the temperature is going to be held constant, so we're not going to have an exchange of energy with the environment. And we're not going to have an exchange of matter. Okay, we're not pumping more gas in. So there's an average amount, or there's a finite amount of energy that's found within that container, within that system. So when molecules hit one another, or when they hit the sides of the container, energy can be transferred when those collisions occur. But we're not gaining or losing any energy. The overall energy of the system stays the same. Okay, we talked about that last week. And then finally, the average kinetic energy of the molecules is proportional to absolute temperature. We talked about this last week too. That when we increase the temperature, we are adding heat. Heat is a form of energy. So if we increase the temperature in our container of gases by adding heat, then our average kinetic energy is going to increase. Likewise, if we decrease the temperature, then our average kinetic energy decreases. So that it's proportional to absolute temperature. So the ideal gas law says how, the kinetic molecular theory explains why. And so we have to consider what each one of those gas molecules is doing. And so it can be, this can really be used to explain all of those gas laws that we talked about. Boyle's law, Charles's law, Gay-Lussac's law. It can be used to explain them all. And it can be used, now that you're kind of thinking about this, we encounter gas laws on a daily basis, whether we realize it or not. In the wintertime, when you go out and your low tire light comes on, well, that's volume and temperature at work right there. So you're looking at an active application of a gas law when your tires become less inflated when it's cold outside. So we are always using gas laws, whether we think about it or not, which most of us don't. So if we maintain this constant temperature, okay, if we increase volume, it causes pressure to decrease. This is an active observation of kinetic molecular theory. So we have a system, and we're keeping the temperature the same. So that means that we have that finite amount of kinetic energy there. We're not giving any more, we're not adding any more energy to the system, we're not taking any away. So we have the average kinetic energy of those gas molecules is the same. So their speed is the same. But when we increase the volume, now they're further apart. They have to go further, they have to move further to have a collision with another molecule. Well, that means there's fewer collisions between molecules, there's fewer collisions between the molecules and the walls of the container. If there are fewer collisions with the walls of the container, then the pressure is going to decrease. Therefore, Boyle's law. Okay, so let me explain that again. We have a system. We have the kinetic energy of the molecules, and by keeping the temperature the same, the average kinetic energy of the molecule stays the same. But if we increase volume, now the gas molecules are spread further apart, which means they have to go further for collisions, which means there are going to be less collisions. Less collisions equals less pressure. So increasing in volume leads to a decrease in pressure, which explains Boyle's law using the kinetic molecular theory. Okay. A temperature increase causes pressure to increase at a constant volume. If we increase the temperature, that means we are adding energy to the system. We're adding heat to the system, therefore we're adding energy to the system. So we get an increase in the kinetic energy and their speed. Because we're not changing volume, the molecules are moving faster, they're colliding with one another more, which means they're colliding with the walls of the container more. And they strike the container more forcefully. So more collisions, more forceful collisions, means that pressure is going to increase. And so an increase in temperature leads to an increase in pressure. So we can apply our kinetic molecular theory to understand the gas laws. Okay. Now, I hope that these lectures have helped you with understanding the characteristics of gases, the different gas laws that we study, the behavior of gases, kinetic molecular theory. If you start working on your assignments or your assessment and get stuck, just holler at me and I'll help walk you through.